Hello everyone, this is our 11th lecture, 11th tutorial. Today we will discuss about normal spaces, regular spaces and those other separation axioms T1, T2, T3. These are our topic for discussion. So before that there is another thing T0 very uninteresting space. So what is the meaning of T0 space? T0 space is a topological space X such that if we take 2 points x comma y, two distinct points from this topological space X, then there should exist an open set either such that x not equal to y for every pair, every distinct point. This is the definition of T0 space. Either there exists an open set Ux such that x Ux contain x, but Ux does not contain y. Okay, either this kind of set exists, that is, for those 2 point x and y, there should exist Ux which contain x but does not contain y, or the opposite thing. There exists open set Uy such that x does not belong to Uy and y belongs to Uy. Okay, either this or the another possibility for this x comma y, there exists some Uy which contains I but not x. Now what is T1 space? It is similar kind of thing, but in this case, instead of either or, this will be and. Okay, there exists open set Ux which behaves like this. It contains x but does not contain y, and there also exists another open set which contains x but uh, which does not contain x and contains y. So instead of either or, this will be the statement will be and, just replaced by and. It is the here condition is stronger than the previous one. Okay, instead of this, it is and for T1 space. Okay, so we have already talked about T0 space and T1 space. Now what is T2 space or Hausdorff space? T2. There is so T2 space, now the condition is more stronger than the previous one. So for any two distinct points x and y, this is the topological space X. For any two distinct points, there should exist. Our demand is there should exist open set Ux, another open set Uy, which separates those 2 points. Okay. So for all x comma y belongs to X, are all distinct. Those 2 points are distinct, or in the right x not equal to y, there exists ux and uy disjoint open set containing x comma y respectively. So if a topological space X satisfies this property, then we will call it the house of space. Now T3 space. So what is T3 space? Here the property is like this. So up to this we have only considered two distinct points. Now instead of considering two distinct points, we'll consider a point and a closed. This is a closed set. F. Okay. Our demand is there should exist open set ux containing x, and there should exist another open set probably u f, or instead of writing in subscript, write it as u, and there should exist another open set v. Disjoint open set containing x and f respectively. Okay. For any point x belongs to x and a closed set f such that x does not belong to f, there exists u containing x, v containing f, disjoint open sets u and v. There is another open set v such that those are disjoint. So u intersection v is in. So instead of considering 2 points, we are now considering a point and another closed set A. So note that T3, so T2 will imply T1, right? T2 will imply T1 because here we have two open sets, but for T1 we only want this one open set. Either this means either this, or there should exist another open set and this point. So T2 will imply T1, T1 will imply T0, but note that T3 may not imply T2. Okay. So what is the problem in this case? So to get this kind of implication, T3 implies T2, this closed set, so its point need to be closed. But in general, this is not, point may not be closed. So T3 may not imply T2. So let me rejoin because there is some internet issue. Okay, I should turn off the camera. Okay, I think now it is better. Okay, so this is all about T3 space, and so we have already noticed that T3 may not imply T2 or T1, but if we add one condition, then T3 will imply T1, T2. So this will be called regular space. Regular space. Regular space means a topological space which is both T3 and T1. Then, then this kind of space is called regular space. So an observation is regular space is housed on T2 space. So T3 may not imply T1, T2, but regular will imply T2. Why? Because I have already assumed it is T3 plus T1. And what is the property of T1? T1 means for any 2 point, distinct point, there exists one open set U which contains that one point and does not contain another point. So if we use this property, then we can prove that a singleton set, every singleton set, T1 will imply every singleton set is closed. Okay. Now every singleton, if we know every singleton set is closed because of T1 property, now let us use T3. So we have already considered X and Y. So now we can treat Y as a closed set because Y is singleton set. So Y is closed, and now use this property for any point, another closed set, distinct closed set. There exists such kind of separation. Open sets, two open sets separating those two different sets. Okay. So from this, it is clear that regular implies T2 space, Hausdorff space. Okay. Now there is another separation axiom. It is called T4 space. So T4 space means instead of considering one point, another closed set, now we'll consider both are closed. Suppose F1 and F2 are two distinct means to disjoint closed set. The demand is there exist open sets U1 and U2 disjoint open set containing those two things. So there should exist open set separating those two things. Okay. For any disjoint pair of closed sets, there exist closed sets f1 f2, there exist open sets u1 u2 such that disjoint open such that f1 containing u1 and f2 containing u2. So this is the definition of P4. Similar to the regular space. Again, regular may not. Okay, regular may not imply uh, it is housed up. Similar kind of issue, a point may not be closed. If we assume the space is also T1 space, then we will call it a normal space. So normal space is same as T4 plus T1. Okay, a space which satisfies those two property T4 and T1, then we call that space a normal space. So those are few separation axioms T0, T1 up to T4 space, and there are some additional assumption which gives us regular space and normal space. So when we write this kind of implication, normal implies regular imply there is T0, T1, T2, T2 implies T1 and T1 implies T0. Okay. This is the direction of the implications. So let us see some problems. This problem says image of a T1 space under a continuous map is T1. So it is true or false? What is the answer? The answer is false because we can create some continuous maps such that image under that map may not be T1, though the domain is T1. The easiest kind of example is this. Consider the identity map from R with discrete topology to R with indiscrete topology. It is continuous because the left side is finite topology. So F inverse of identity inverse of there is something is open here will also be open in discrete. Therefore, this is continuous, and image of the identity map is R. Okay, but note that R with discrete topology, this is T1 space, right? Moreover, this is T2 space because for any 2 point X and Y, I can take the open set as this singleton set, X belongs to this singleton set and Y belongs to this singleton set. Those are disjoint open set which contains X and Y respectively. But R with indiscrete topology, this is not a T1 space, right? There are only two open sets, the topology is empty and R. Now if we consider any two point x and y, then note that we do not have any open set which contains x but does not contain y, because there is only one non-trivial open set which is R, and R contains both x and y. We have already assumed x and y are different distinct points. So from this counter example, it is clear that image of a T1 space may not be T1, right? Under a continuous map, image of a T1 space is not T1. So this is false. Exists T1 space if and only if singleton sets are closed. So what is the answer? It is true or false? Answer is true. This is one of the very important property. We always desire that a singleton set should be closed, and T1 space is enough to consider for this kind of property. Okay, so let us see why this is the case. Let x is T1. So this implication T1 will imply singleton sets are closed. So we have assumed x is T1 space, right? We need to prove that this singleton point x is closed. Okay, and let x belongs to S. Now consider all those points from the complement. So y belongs to x minus x, right? Then there exists some open set uy which contains y. There exist open sets uy such that y belongs to uy and x does not belongs to uy. Okay, so for any distinct point y, there exists uy which contains y but does not contain x. Now take all those open sets, right? So take union of uy. Y belongs to x minus x. So arbitrary union of open set is open. So take this and denote it by some v. Okay. Then v is open because we are taking arbitrary union of open sets which is open. And note that v is nothing but v is itself x minus x, right? Because we have already chosen everything. Note all those points x minus x already containing this because of this property. I have not only chosen the point but also a neighborhood. So automatically everything y belongs to x minus x also containing this uy, and this side is also clear, right? Because uy, that uy does not contain x. So those two side is clear. Therefore v is open. So x minus x is this is open. Hence this is closed. Okay. Similarly, the this side is also easy to show. Okay, if we consider this kind of thing, Then if we consider a singleton set is closed, suppose this singleton set is closed, this X is closed, then for any 2 point, X is closed means this X minus X, this is open, and this contains this Y but does not contain X, right? Singleton set is closed, so X is closed, let X not equal to Y, then X minus X is open, so I should write this, and X belongs to X minus X, sorry, Y belongs to X minus X, but Y, but X does not belong to X minus X. So the desired property is satisfied. Okay. So T1 space is if and only if singleton sets are closed. Now this question says X is finite and T1 space, then X is discrete. Is it true or not? Then X must be discrete. So the answer is yes, this is also true. Why? Let us see. So X is T1 space means X is T1. This implies all singleton sets are closed. And we know that finite union of closed set is closed, right? So all finite sets are also closed, because if we take a finite set, suppose F is some finite set, for example x1 up to xn, if we consider this finite set, this can be written as union of xi's, this singleton set I equal to 1 to n, right? Therefore all finite sets are also closed. Finite union of closed set, hence it is closed. So from here it is clear that since X is finite, all any subset is finite. Since X is finite set, therefore every subset will be also finite, right? Is closed because of this by star. Complement of those subset. So every subset means the collection of closed sets is the power set Px. Hence, if we take complement of each of those sets, then that will be open, and it will be also the same power set, right? Every subset is closed, therefore every subset will be also open. Because from here collection of closed set is power set Px, and if we take again complement of each of those elements, then we will get the same power set, right? So consider this topology. Here the topology is defined on the set AB, and tau contains empty, the whole set, and A. Then this space is which of the following is true? This space is T0, T1, T2, and T3. So we note that if we consider two distinct points in this space, so one point is A, another point is B. There is only two distinct points. So there is a open set which contains A but does not contains B, and this is the property for being a T0 space, right? So this space is T0 space. It is clear because there exists some kind of separation, but there does not exist any open set which contains B but does not contain C. There is no such open set. Only non-trivial open set other than empty and X whole set is A. So there is no open set which contains B but does not contains A, right? So though it is T0 but not T1 space, since it is not a T1 space, it is not also T2 space, because T1 will imply T2. So T0 is okay, T1 is false, T2 is false. Now what about T3? So what are the closed set in this topology? So closed sets, here the closed sets are complement of empty is X, complement of X is empty, complement of A is B. So now if we consider A as a singleton point, B as a closed set, then we don't have two open sets which separates those two separates this point from the closed set B, right? Because there is no open set which contains B but does not contain A. So it is again not T3 space. So true or false? R with we are considering the set of real number R with cofinite topology. The statement is that this is T1 space but not a T2 space. So let us see if this is true or not. So if we consider cofinite topology, note that the singleton set, if we take singleton set, then this is closed. Why? Because the complement R minus this singleton set is open in cofinite topology, right? Cofinite topology. Complement of finite thing that must be open in cofinite topology. So from here it is clear that every singleton set is closed. Singleton set is closed. Therefore, this is T1 space. So the first part is okay. R with cofinite topology CF is T1 space. Now what about T2ness? Will it be T2 space or not? So T2 space demand for any two distinct X and Y, for all X not equal to Y, from the topological space X, there should exist open set Ux containing the point X and Uy containing the point Y. Is it possible? So let us assume this. Suppose there exist open sets ux, uy containing x, y respectively. Okay. So now the problem is, what will be the problem? So those are open sets. Therefore, complement of um, the problem is those two open set cannot be disjoint, right? Because ux contains almost everything except some finitely many points. Uy contains everything except some finitely many points. So that will be the issue. Okay. The problem will be they must overlap. So we'll prove that their intersection cannot be empty. So this is finite. Uy complement is also finite. Therefore, that will imply their union is finite. That will imply, by De Morgan's law, this is same as ux intersection uy complement. It is finite set. So ux intersection 2y, this cannot be empty, right? Because if this is empty, this should be same as r, but r is not finite, right? So this is a contradiction, not a contradiction. So from here it is clear there does not exist disjoint open sets ux and uy which contains x, y respectively. Though there are some open sets, but those open sets cannot be disjoint. Hence, R with cofinite topology is not T2. So this answer is true. Now question number 6. A convergent sequence in a Hausdorff space converges to an unique point. If possible, assume the sequence, there is a sequence xn which converges to two distinct points x, y respectively. Okay. So we are assuming that xn converges to x and xn also converges to y, x, y are different points. So what is the meaning of convergence? Convergence means if we take a neighborhood of the limit point, that is this point, then it contains almost everything except some finitely many terms of the sequence. It has everything, right? It contains tail of the sequence. So xn converges to x means a neighborhood u of x contains xn for all n greater or equal to k, for some k, right? Similarly, xn also converges to y means the same type of thing. There exists neighborhood p of y containing yn for all n greater equal to, instead of k there is exists a different natural number, k dash belongs to n for some. Now this is a Hausdorff space, so we may take disjoint neighborhood, right? So there exists UP disjoint open sets containing xy respectively. By Hausdorff's, there exists this kind of open set. So U is, so note that U contains almost everything except some finitely many points. U contains all those xn, and similarly V contains all those xn's. Sorry. If we take the maximum of k comma k dash, then xn from 1, take maximum of k comma k dash, and denote this by some L. Okay. Then xn belongs to U for all n greater equal to a, right, by U. And similarly xn belongs to P for all n greater equal to L by U. But this is a contradiction, because U and P are disjoint open set. It is a contradiction. This is the point where the contradiction arises. So there cannot be two different limits of a sequence. The limit is unique. So again, the answer is 2. In this problem, we are considering a sequence 1 by n, where n belongs to natural number. So the question is, this sequence converges to 0, 1, minus 1, or nothing? It does not converge. In real number, we have already seen that 1 by n, this kind of sequence converges to 0. But in this case, we are considering indiscrete topology, right? So, for in this, just a small comment. Instead of cofinite topology, the same argument can be applied for co-countable topology. Okay. So, in this case, note that what is the neighborhood of 0? Neighborhood of 0. It is, there is only one possibility, because empty cannot be neighborhood of a point. So it is R. R is the only neighborhood, and R contains, the real number contains all those 1 by n, not only tail of this sequence, it contains everything. Okay. Therefore, so every neighborhood of 0 contains 1 by n for all n. Instead of some n greater equal to k, it contains everything. Okay. Therefore, this is our sequence. Therefore, xn converges to 0. And similarly, we can prove the same argument can be applied for all those other points. Similarly, xn converges to 1 and xn also converges to -1, because the only neighborhood is real number r. R is the only neighborhood, and the every neighborhood of 0 means there is only one neighborhood. R contains all those x, right? So neighborhood of 1 is also R, and it contains everything. Therefore, xn converges to 1 and xn converges to -1 as well. The options are A, B, and C. So let me give a similar kind of problem. Seven dash. Consider R with discrete topology. Then the sequence 1 by n converges to option A 0, B 1, C -1, D nothing. Suppose this sequence, let xn equal to 1 by n, then if xn converges to some x, this implies then every neighborhood of x contains xn for all n greater or equal to k. Okay? K is some natural number. Natural number. Now consider the neighborhood this x. Okay, so x belongs to this singleton set. Clearly, this singleton set does not contain any other thing, any other element other than this x, right? So it cannot contain infinitely many terms. All those x and n greater or equal to k. Therefore, it is clear this neighborhood does not contain infinite, cannot contain infinitely many points. So it cannot contain all those xn for n greater or equal to k. Therefore, xn cannot converge. Does not converge. So those are two extreme topological spaces. In this one space is indiscrete topology where every sequence converges, right? And another situation is discrete topological space where almost no sequence. So either the sequence is essentially constant. If this is not the case, then no sequence can converge in this space. Converge in this space, okay? So just this problem is useful to see that this problem is useful to see the fact is that if if the topological space is not T1 space, sorry, it is not T2 space, then there can be multiple limit of a sequence. So limit may not be 1 by n also converges to 0, also converges to 1, and also converges to minus 1. Okay, so if the underlying topological space is T2 space and a sequence converges to a point, then the point must be U. Okay. Question number 8. Again, true or false. Here it says every metric space is normal. Is it true or false? So the answer is true. Okay. Every metric space is actually normal space. There are different proofs for this, but one proof which is more algebraic is like this. So consider f from x comma d be a metric space. Consider f which is a map from x comma d to, okay, are with usual topology. Defined by, so to prove something is normal or not, we need to choose two disjoint open-sets, right? So a topological space X is normal or not, how do we check? We take disjoint open set A and B, and we need to see if there exists some open set which separates those closed sets. We also need to assume those two closed sets, and A comma B are disjoint closed set of X. Okay? So we define the function by fx equal to distance from A to distance from B. Okay. So in this case, okay. Okay, so this function is continuous. F is continuous. Okay, we need to check, but if we assume F is continuous, note what is happening. If we restrict F over A, so if we take any point, if we take some A, then distance from this set A belongs to this A, right? So distance from A to this capital A is 0. How the distance is defined? So recall, distance x comma A is nothing but infimum of dx comma A, where A belongs to A. Right? This is how the distance is defined. So instead of x, if we choose an element from A, capital A, then dA 0 is the minimum thing. 0 is the lowest possible thing, right? because distance is always greater or equal to 0. So f restricted over a is actually 0. And similarly, f restricted over b is actually 1. But it's the same kind of reasoning. If we take an element from b, this is db comma a, and b comma b, this is actually 0. B distance from this b to capital B is 0 if we choose an element from capital B. So those two are same. So cancelling each other, it will get 1. This is how we are getting it. Now, so if we assume f is continuous, then observe that f inverse, so 0 belongs to this 0 comma half, this neighborhood, sorry, minus 1 comma half, right? Or 0 comma half, whatever we take. This does not 0 comma, sorry, not 0. 0 belongs to minus 1 comma half. This open set. And 1 also belongs to half comma something, half comma 1 plus something, 1 3 by 2 or something like this. So those two are disjoint open set. Now f inverse, take u equal to f inverse this minus 1 comma half, c equal to f inverse half comma 3 by 2. Since those two are disjoint, if we take pre-images, that will also be disjoint, right? No, u intersection v is disjoint, right? Their intersection is empty. Therefore, and another interesting thing is that and a containing u, right? Because why this is the case? Because 0 belongs to u, right? So sorry, because if we take any element from this a, then the value, if we apply f, then we'll get 0, and 0 belongs to this neighborhood minus 1 comma half, right? The thing is that 0 belongs to this neighborhood, so f inverse of this containing this is the thing. So f inverse 0, a already contained in f inverse 0, right? Therefore a containing this f inverse minus 1 comma half, which is denoted by u. So a is a containing u, and similarly b containing v. So from all of this, it is clear there exists two separating two open set which separates the closed set, disjoint closed sets, n, right? So u and v are those open sets. Therefore, X is known. So every metric space must be a normal space. Okay. X is housed up if and only the diagonal is closed. So is it closed? So how the diagonal? Here I have not proved f is continuous, but the proof is very easy. We only need to see that this function is continuous because division, addition, division, those kind of thing is continuous if we consider the codomain is uh, Euclidean space, right? So the only thing we need to prove distance is continuous function, which is also very easy. Just use the triangle inequality. Okay, triangle. If we use triangle inequality, we can easily prove the distance. We only need to consider this function gx equal to d of x comma y. Just prove this is a continuous function. Gx minus gy. Just estimate this gx minus gy. Estimate using triangle inequality. It is very easy to see this. This is a continuous function. X is Hausdorff space if and only if the diagonal is a closed set. Okay, let us see if this is true or not. Let X is T2 space. So what is delta? Delta means this kind of thing, x comma x, such that x belongs to x. So those are diagonal elements. So we have assumed x is Hausdorff space. Now we need to see the diagonal is closed. So it is enough to show x minus diagonal is open, right? But so this is open. So let x comma y, this point belongs to this x minus diagonal. Okay. X minus diagonal means x not equal to y. By Hausdorffness, Hausdorff and T2 are same. Hausdorffness, there exists open U V containing x comma y respectively, such that their intersection is empty, right? Consider the neighborhood U cross B of the point x comma y. The claim is that U cross V, sorry, diagonal is not a subspace of x. This is actually subspace of x cross x. Then U cross V entirely lie in x cross x minus diagonal. Why? Because there is no element which looks like a comma a. Okay, because if we assume some a comma a, this is rough work. If a comma a belongs to U cross B, this will imply a belongs to U and also a belongs to B. But U intersection V is empty, so this is a contradiction. Okay. So we have successfully found a neighborhood which neighborhood of the point x comma y, which containing the complement of the diagonal. Therefore, complement of the diagonal is closed. X cross x minus delta is, sorry, this is open. There exists a neighborhood which also containing that set. And similarly, you can show the reverse direction. The proof is very easy. For the reverse part, if we assume this delta is closed, same idea, there is nothing new in this case. Then x cross x minus delta is open. That means for any point x comma y belongs to x cross x minus delta. So if we assume let x not equal to y, then x comma y belongs to this, right? And by openness there exists open set U such that U contains x cross x comma y and open neighborhood of x comma y, which is U, and U also containing x cross x minus delta. Okay. Now take the projection. Okay. So pi 1 U and pi 2 U, those are, so the idea is like this is the space x cross x, this is x cross x. Now we are deleting this diagonal line, then the claim is that this is closed. So we have chosen a point x not equal to y, something like this, and by openness there exists a neighborhood which does not intersect the line, right? So you are containing this complement of the diagonal. Then take the projection. One projection will be this and another projection is this. Okay. Then our claim is that those two projections are also destroyed. This is pi 1 on the first coordinate, this is pi 2. So pi 1 is the projection x cross x to x defined by pi 1 of x comma y equal to x. Similarly, pi 2 will be pi 2 of x comma y is y. Those are continuous. So there okay, there is some issue. For example, we don't know if pi 1 u will be open or not. Pi 1 of u may not be open, right? Yes, this may not be true. Okay, so just modify the neighborhood. We can choose, in particular, we can choose some, the neighborhood should look like this, because for product topology, basis looks like some open set cross open set. So we may forcefully choose the neighborhood like u cross v. Okay. So that u cross v. Then the claim is that because that idea fails because those projections may not be open. So instead of taking arbitrary neighborhood, we can always take some kind of u cross v. Okay. Now u intersection v is non-empty, and x belongs to u. This is by definition of Cartesian product. Y also belongs to u. So here we need to see why this is the case. So if some x belongs to u and v, some a belongs to u and v, then the same kind of issue will arise. A belongs to u and a also belongs to v. This will imply a comma a, this pair will belong to u cross v. But this will be a contradiction because of this fact. Contradiction, right? Contradiction. Therefore, we have successfully found neighborhood uv of x comma y such that their intersection is empty. Sorry, intersection is empty. X is so this is one of the characterization of Hausdorffness, and moreover, we can prove using this fact. We can prove graph x comma fx containing x cross y is closed. If we assume x, y both are Hausdorff space and f is a continuous map, then this is called graph of the function says that x belongs to x. This is actually closed set. Okay. Yes. If we take any kind of graph, then that will be a closed set. This is very useful. For example, we have used this kind of property for connectedness. Those are closed or not. Probably we have used. The idea is very easy, similar kind of thing. So here we take this continuous map. One side is identity and one side is f. And sorry, take x cross y to yes to y cross y. The first one is f, second one is identity on y. Then this is continuous. Exclusively it can be proven. One property is if a map from x to y, another map from x dash to y dash, those two are continuous, then the product of the map will be also continuous. Very easy to prove. Just take a pair, a product u plus b, and take the p image. Okay. Now let us see why this is the case. Graph is closed. So f cross identity inverse. So we have assumed those y is Hausdorff. We have assumed y is Hausdorff, and product of Hausdorff spaces is Hausdorff. Okay. So this is hypothesis. Y is Hausdorff. It is given. Okay. So if we consider f cross identity inverse of diagonal, diagonal means diagonal of y. So delta is a subspace of y. So this is actually GF. Why? Because suppose x comma y belongs to this, that is f cross identity applied on this belongs to diagonal. That means fx should be fx comma y belongs to diagonal, right? But that means y equal to fx. So we are considering all those x comma y such that y equal to fx, and this is the definition of graph, right? So by continuity, inverse image of closed set is closed. By continuity, GF is closed. Okay, so this is very useful property. Graph of a continuous function is closed. Given the codomain is housed out. If y is housed out, then the graph is closed. There is one thing I need to say. In the previous tutorial 10, I have said something wrong. So for the definition of one point compactification, so there is some contrary thing. I have said that compactification, if we given a locally compact housed space X, we can make it compact by adding a point. So X hat is X union infinity, and we topologize X hat, topologize by this. So open sets are either U or X minus some compact set union infinity, right? Either U, where U is open in X. So if we define the topology on X hat by this, then X hat becomes a compact set, and X hat satisfies the properties of one point compactification. First one is we have only added one point. Another is X hat is a compact set, compact space which contains X, but compact housed space. But one problem arises if we take the definition as this. So closure of X may not be X hat. Okay. So this may not be true. So this is true if X is not compact. Because if X is itself a compact space, then closure will be itself, right? In this case, this compactification is not the same as uh, the definition which is given in the book. Okay, so just to clarify, this is same as one point compactification given in the book if X is not compact topological space. X is locally compact housed out but not a compact. Otherwise, there is some issue, because if we assume X is not compact, then infinity will be a limit point, right? Infinity of X hat will be limit point. Take a neighborhood of infinity, which will look like X minus compact set. It contains a point other than infinity, right? This neighborhood contains a point other than infinity. This is possible if X minus compact set is non-empty. This is non-empty, right? So this is non-empty. That will be true if X is not compact. Otherwise, if X is compact, then infinity itself will be a neighborhood. It is like just take the compact set. If X is itself a compact set, then take the compact set and include a point and define the topology as the previous one, and just take one additional open set infinity. Okay, so take infinity. So, and also we need to take union of those union with the previous open set. So this is the problem. This closure of X may not be same as this. So, but in the in the examples also, those are actually non-compact spaces. The one-point compactification of the previous examples, for example, we have discussed uh, open unit disk or something like this kind of interval or union of two open intervals. Those are actually non-compact space. For compact space, the one-point compactification is means using this does not fit with the definition given in this. So we may ignore that case actually. One-point compactification of complex because this closure of the space, underlying space, is not same with X set. If the space, given space is itself a compact space. So that is the problem. Otherwise, everything is okay. Okay. So another thing I should say, there are some important characterization for T T2 spaces, T3 spaces. So for T2, so what are the characterization? Let me write explicitly. T1 space. T1 space means for any 2 points. So let me write all those cases. T1 spaces, T2 space, T3 space, and another is T4 space. Those are our separation. So for T1 space, it means for two distinct point xy, there should exist some open set like this, separating one point from another. This and also the reverse one. Okay. For T2 space, let me write all those cases. So for T2 space or Hausdorff space, there should exist two neighborhood of x comma y, disjoint neighborhood, which is separating those 2 points. And for T3 space, for a distinct point x from a closed set f, there should exist two neighborhood which is separating those separating the point x from the closed set. And for T4 space, for any two closed set f and f dash, there should exist two open set which is separating those two closed sets. Okay, open set containing f and f dash separating. So for T1, the equivalent criteria is if and only if singleton sets are closed. For T2, the equivalent criteria is diagonal containing x cross x. So x is the space which we are considering. X cross x is closed. So we are writing some equivalent criteria in terms of some closure or some closed properties. Okay. T3. This is equivalent to saying me draw. So if we take some open set U and a point x belongs to this open set, there should exist some open set U which contains some V which contains X such that closure of V also contained in U. Okay. So for every open sets U and a point X belongs to U, there exists an open set open neighborhood V of X such that X belongs to V containing closure of V containing U. Okay. So this is very easy to see. Just to prove this side, this implies this. So take the point X and take the point complement of, take the closed set as complement of U, because U is open, so complement of U, this interior thing will be closed. Sorry, this is the set U, so complement will be this. Okay, take this and this point, so those two are disjoint, and apply this property. This is very easy to see. This direction is the obvious one, and this is also easy to observe. Just write and prove. Very easy to prove. Okay. And for T4 space, there is similar kind of property in terms of closure and open sets. So again, consider an open set U, another open set U. Suppose this open set is so instead of U, let me write as G, because I will use V. Okay, those are two open sets. Then for every open set U and V with D containing U, there exists G open set G such that U containing G containing closure of G containing sorry, V is the smallest. So this is V. There should exist some U and closure of U. This is our U and this is closure of U. Okay. So this kind of thing, sorry, not U. U is already there. It is G and closure of G. So this should hold. Okay. So again, those are very similar. Even the proofs are very similar. And another useful thing is that if fact how the space is actually normal. Means it must be T4 and T2. Every compact house the space is normal. This is also very useful property. Okay. So those are the main facts about this separation axioms. I'll stop here. Thank you.